who was ahead of what. And Charlie's going to talk about one of my favourite areas of mathematics, optimal transport theories. So over to you, Charlie.
Thanks, Chris. Thank you very much for inviting me to talk at this event on knowledge exchange, and as in this talk, applications push forward mathematical theory and actually shape that theory, which the first few talks have really wonderfully demonstrated. So Chris, I hope I can do justice to one of your favourite applications of optimal transport. So optimal transport theory is a mathematical theory of how to move mass from one configuration to another in the most efficient way possible. And it's recently found applications in many different areas, all the way from physics to meteorology to materials science, data science, and beyond. In this talk, I will focus on just two such applications. These are weather forecasting and modeling steel. And in both of these applications, the story I'd like to tell is how questions that really came directly from the applied communities working on these problems gave rise to brand new mathematics in the field of optimal transport. So, what is optimal transport? Optimal transport starts with a French mathematician. So very much like in the last talk, it starts with a French engineer, in fact, someone by the name of Gaspard Monge. Monge was around in the mid-1700s. And when he was a teenager, he attended a military engineering college. And while he was at that college, one of the tasks that was given to him was to find the most efficient way of transporting or of building embankments around a fortress. And legend has it that Monge found such an efficient way of doing this that his superiors didn't believe it was possible until they saw it with their own eyes. He later wrote a paper on his methods, the English translation of which is On the Theory of Cut and Fill. And the problem that he posed there has become, this is really the birth of optimal transport theory. So right from the start, we go from a very concrete application, building these fortresses, or the embankments around the fortress, to a mathematical problem. So here's the statement of the problem. We have a source space X. You can think of that as just a subset of RD, and that's equipped with a probability measure mu, so a measure with mass 1. And that describes the initial configuration of mass. Then we have a target space Y, and that's equipped with a target mu, also a probability measure with mass 1, and that describes, in Monge's case, the shape of the embankments that he wanted to build. Another way of describing how we would move mass from X to Y, we do that using a map T. The T is said to be admissible if for any set A in Y in our target space, the mass of the pre-image under T of that set is equal to the mass of the set A itself. So in other words, mu of the pre-image under T of A is equal to nu of A for all subsets A of Y. And the shorthand for this is that T pushes mu forward to nu. That's what this hash symbol means. So this is the constraint in the Monge problem. It says that we move mass in a way that doesn't create or destroy mass, it doesn't split mass, and we create the embankments that we want. The Monge problem is a constrained minimization problem. That's the constraint. The objective, the thing that we're trying to minimize, is the total transport cost. That's the integral of some cost function in C, which is to be defined in the problem. C tells us how much energy, how much effort it takes to move mass from a point X to its target point T of X. And then we integrate that cost over the source space with respect to the source measure mu. Yeah, so the Monge problem is to minimize the transport cost over all admissible transport maps. And the minimum value of that transport cost is called the optimal transport cost. And if a minimizing map T exists, that's called the optimal transport map. One example, one kind of special case is where x and y are subsets of the same RD, and the cost function is the square of the distance between 2 points. This is the kind of classic example which relates directly to Monge's problem. In fact, Monge looked at the just the distance between points, but when you have a square distance, the cost function is then strictly convex in the distance between x and y, which is a bit nicer mathematically. But the point here is that the square root of the corresponding optimal transport cost is actually a metric on the space of probability measures. And that's what's called the Wasserstein-2 distance. And we'll see that in a couple of the applications later in the talk. So immediately, there are two natural mathematical questions here. For which cost functions, source measures, and target measures do optimal transport maps exist? And if they exist, can we characterize them? Can we say what their structure is? Now, the Monge problem stayed open for over 200 years. During that 200 years, a lot of progress was made within optimal transport itself. So notably, the Soviet mathematician Leonid Kantorovich defined a relaxation of the Monge problem and showed that solutions to that existed. But there was still a gap between that result and a result on the Monge problem. And among other things, numerical weather prediction became a thing. So that brings me to the first application that I'd like to talk about, which is weather forecast diagnosis. And we'll see how optimal transport is involved in this in various different ways. So the aim of weather forecast diagnosis is to understand where and why forecasts are going wrong. And the approach to do this is to compare forecasts that have been made to outputs of simplified models of the atmosphere. One such simplified model is the semi-geostrophic, or SG, equations. And they model the formation of weather fronts in the atmosphere. Weather fronts are boundaries between regions of warm air and cold air, and you'll recognize them as these blue and red lines that you see on the maps. So here's a statement of the semi-geostrophic equations as we understand them today. So it's a coupled transport equation. The transport velocity in the transport equation is defined through an energy minimization problem at every point in time. And you might notice that this energy minimization problem is exactly an incarnation of the Monge problem. It's a Monge problem with the quadratic cost. For some context here, the source measure, mu, that represents the fluid density, is taken to be constant in this model because this particular model is the incompressible semi-geostrophic equations. The transport map that you find maps from the fluid domain into a domain of momentum and temperature. And the thing that we're advecting in this transport equation, it's a time-dependent probability measure, and it represents a physical quantity called the potential vorticity. But mathematically, and the kind of message that I want you to take away from this slide is that this is a model for large-scale dynamics in the atmosphere, and it's a coupled transport equation where the transport velocity in that equation is defined by solving the Monge problem. Okay, so meteorologists Mike Cullen and Jim Purser studied these equations in a paper of theirs in 1984. They were working at the UK Met Office at the time, and they developed something that they called the geometric method for solving the problem when the potential vorticity is discrete. They realized that in this case, the optimal transport map takes the form of the gradient of a convex and piecewise affine function, and that actually goes back to a result of Alexandrov. So here I've taken a screenshot of a figure from that paper by Cullen and Purser, where they sketch the kind of shape of this convex function, whose gradient is the optimal transport, the solution of the Monge problem. But this left them with a question. Is there a continuous limit of these discrete solutions? Is there some underlying PDE? I mean, I've already shown it, but this is not really in chronological order, I suppose. Is there a continuous limit of these discrete solutions? Is there a PDE that governs these large-scale dynamics? So Mike Cullen presented this question to the mathematical community. And through several mutual connections, he was put in touch with the French mathematician Jan Brenier, who it turns out had the key ingredient to solving this problem. So I'll first tell you what Brenier's theorem is. And this was a huge result in optimal transport theory in its own right, aside from many applications in weather forecast diagnosis. This was published in 1991. And the theorem is that for any measure mu, which is absolutely continuous with respect to the Lebesgue measure, and a cross function, which we take as the squared distance function, the Monge problem has a unique solution, which is the gradient of a convex function. So this corresponds directly to what Cullen and Purser sort of predicted in their paper. But remember, Cullen and Purser only did it for discrete target measures. Brenier's theorem is stated for a general target measure, as long as the source measure is absolutely continuous or has a density. Okay, so the story goes that Mike Cullen and Jan Brenier met actually at an Isaac Newton Institute program in 1996. That's where the kind of start of this collaboration took place. And 2 years later, Benjamin Brenier proved the first rigorous theorem on the existence of solutions to the semi-geostrophic equations. They showed that solutions exist for LP initial data. And this gave rise to a huge amount of work on the semi-geostrophic equations and all its different variants. So we've just seen the incompressible semi-geostrophic equations where the density is fixed. There are variants where the density is not fixed, it's also dependent on time. For example, the compressible semi-geostrophic equations that was studied by Cullen and Marufi in 2003. There's actually a very recent preprint by Theo Lavier and collaborators on the compressible semi-geostrophic equations. The equations that I stated are in the space of momentum and temperature, and one of the huge challenges for mathematicians was to actually try and take solutions that were found there and pull them back to physical space, so kind of spatial coordinates, Eulerian solutions in physical space. And this problem was solved by the group of Ambrosio, Colombo, De Filippis, and Figali in 2012. And that used theorems on the regularity of optimal transport maps. So in addition to just results on the semi-geostrophic equations and generalizations of those, Ambrosio and Gangbowen in 2008 noticed there was a Hamiltonian structure to the semi-geostrophic equations. And they then generalized this, defining the notion of a Hamiltonian ODE in the Wasserstein space, this metric space of probability measures. So this was really a pure result that came out of the study of the SG equations, and it uses the theorem of Benjamin Brenier as a blueprint. Okay, so just to conclude this first half of the talk on weather forecast diagnosis, I'd like to quickly explain an ongoing collaboration that I'm actually involved with. And this is to do with defining the background state of the atmosphere. This is a collaboration between myself, Mike Cullen, who I've already spoken about, David Bourne, who's a mathematician at Heriot-Watt University, and John Methven, who is a meteorologist at the University of Reading. So another Isaac Newton Institute program, actually, Mike Cullen introduced me to John Methven because he knew that John had a problem that could be solved using optimal transport. So John is interested in defining the background state of the atmosphere because by doing that, okay, long story short, it's related to weather forecasts with lead times of from 2 weeks up to 3 months, so sub-seasonal to seasonal forecasts. And kind of the first step in the analysis of improving those forecasts is to define a background state of the atmosphere. So when I met John, he had a physically motivated definition for this. He even had a way of computing these background states from real data. But he had two problems. One was that he didn't know whether his definition made rigorous sense. Did these background states exist? And if they did, were they unique? And secondly, the numerical results that he had, the numerical implementation, it didn't always work, and we weren't sure why it didn't work. So we managed to prove that indeed this definition that John had was rigorous, and I'll quickly explain how it works. So we have a source space, which again represents the fluid domain. We have a target space. We want to find a map between these two, an optimal transport map. But this, it turns out, was actually a generalization of the modeling problem, because in this problem, we know what the target measure is. That comes from real data. But the source measure is an unknown of the problem. So not only do we have to minimize the transport cost over admissible transport maps, we also have to minimize over a class of source measures. Each measure in that class is defined by a surface representing a free pressure surface. Okay, so this was a really satisfying project to work on. And it turns out that our method of proof gave rise to a numerical method. So here we see the feedback all the way from an applied problem into a pure mathematical problem, and then back to the application. And so with that method, we've been able to compute these background states of the atmosphere from a time series of climate reanalysis data. And yeah, this is ongoing work. I'll actually be starting a position in Reading, working exactly on this project in September. Yeah, so I very much benefited from this this knowledge exchange and this collaboration. Sip of water. Okay, now on to the second application I want to talk about, and this is on modeling steel. So this, thanks, Chris. So this application and collaboration was between the company Tata Steel and, again, many people from the optimal transport community. So steel, the structure of steel is grain-like. If you zoom in and you look at steel, then it's formed of these grains, which are roughly polygonal in shape. So Tata Steel are interested in modeling how the properties of steel depend on the grain structure, because the grain structure is something that they can somewhat dictate when they form steel. The approach of doing this modeling is first to model the microstructure. So that means generating tessellations that are similar to the grain-like structure that you see in steel. And then the second phase of this modeling approach is to assign physical properties to each of these grains and simulate mechanics. So how does this steel react to different forcings? We'll be talking just about this first phase, modeling the microstructure of steel. And there, the challenge is to generate tessellations with prescribed geometric properties. So, for example, Tata Steel might want to specify the grain volumes or the spatial distributions of these grains with different volumes. And you guessed it, the mathematical tool that we use here is optimal transport. Specifically, the tessellations that we obtain by using optimal transport are called Laguerre tessellations. So I'll take one slide to explain what a Laguerre tessellation is, and then I'll link that back to optimal transport and this problem of modeling steel. A Laguerre tessellation of a set X, subset of Rd, generated by the weighted points Yi with weight Wi, is a partition of X into cells Li defined in the following way. For an index I, you have all points in X whose square distance from yi minus the weight wi is less than or equal to the square distance to yj minus the weight j. So each of these inequalities defines a half space, and a single Laguerre cell is the intersection of many half spaces, which means in 2D these are convex polygons, and in 3D they're polyhedra. And these are often used by engineers to model metals and foams. Okay, so on to a challenge that was directly posed by Tartar Steel. Can we generate tessellations with cell volumes that are specified, so cell volumes VI? And the solution is actually to solve another incarnation of the Monge problem. So here's why. Let's say we have a space X that's representing kind of the domain that we build our steel in. That's a subset of our 2 in this case. And we equip it with the Lebesgue measure. And then we define a discrete measure. There's a sum of Dirac masses at arbitrary points. I'll come back to that. Arbitrary points yi with weights vi, the specified cell volumes. Then the optimal transport map from u to this discrete measure nu is piecewise constant with respect to a Laguerre tessellation, and it just so happens that Laguerre tessellation is formed of cells that have exactly the prescribed volume. So this comes from the push-forward constraint from the Monge problem. It's a discrete analog of that. So this problem was studied by Hitagawa, Merigo, and Tibbett. They developed a fast algorithm for solving this, and that was used by Born, Koch, Groper, and Spanier in the application of modeling steel. Okay, so that's the first challenge. And here there's kind of no new mathematics. This was known, but this was like the start of the collaboration. And now you can see that because these locations yi were chosen arbitrarily, we have a bit of wiggle room to then define the target measure in such a way that we can control the spatial distribution of these cells. So that's the next challenge set by Tartar Steel: to generate tessellations with given cell volumes and cell centroids, so centers of mass. And the motivation for this is that you could take an image of steel. Here it's colored so you can see the different grains. And you might like to model that. And so one approach would be to try and fit a Laguerre tessellation to this image so that the Laguerre tessellation has the prescribed volumes and centroids. It turns out that to solve this involves solving what's called a Wasserstein projection problem, which I'll go into slightly more detail in the next slide. So the two sort of pure mathematical results that came directly from this are, firstly, a Laguerre tessellation is uniquely defined by its volumes and centroids, the volumes and centroids of its cells. So this was a result by Bourne, Pierce, and Roper, a recent result actually, last year. So that says if I give you volumes and centroids, there is at most one Laguerre tessellation whose cells have those volumes and centroids. But it's not guaranteed that a tessellation exists. So that was left as an open question, which was then answered in a follow-up paper where the authors showed that the volumes and centroids such that there exists a corresponding Laguerre diagram are actually the exposed points of a particular convex set. So this brought in aspects of convex analysis, of course, optimal transport, and calculus of variations. And this is what corresponds to the Wasserstein projection problem, which I'll talk about just to give you an idea of the maths that was involved. So first, the definition. A measure nu is said to be dominated in convex order by another measure mu. We denote that with this curly less than or equal to sign. If for any convex function phi, the integral of phi against nu is less than or equal to the integral of phi against mu. So to solve this problem that Tartar Steel posed, you solve the following projection problem. You're given volumes and centroids, use them to build a discrete measure in the kind of the only way you can. You put volumes VI at positions CI, and then you project this discrete measure onto the space of all measures that are dominated in convex order by the measure mu, which in this case is the Lebesgue measure on your domain X. Yeah, so that's the projection problem. Okay, so with that, I'll conclude. I talked about two applications among many applications of optimal transport, where the application has given rise to mathematics. Yes, and I will conclude the talk there. Thank you.